Alright, so we've got two guys. They have identical boxes on identical surfaces. The only difference with each scenario is that Art is pushing his free body diagram like this, and Bill is pulling, not pushing his free body diagram, pushing the box. So I'm going to draw my free body diagram right here. So each has the force of gravity. Each has the same force of gravity. They both have a normal force. Art is pushing both down and to the right. So the down would be like your F sine, and the to the right would be your F cosine. And then Bill is pulling, so that would be both to the right and up. So F sine and F cosine. Now, it does not specifically tell me if friction is there or not, but it tells me that Art's does not move. So if you are pushing it and it does not move and there are no other forces acting on it, right, it's not being pushed back or something, then there must be friction holding it in place. So that would be the friction force, and this is also the friction force. Now the scenario is that Bill's moves, but Art does not, and I want to know why his moves, but his does not. Because they have the same force at the same angle, so this is the same for both of them, right? But Bill's, this one moves, which means this F cosine is enough to overcome friction, whereas for here, this one is not moving, it is at rest. So this F cosine, the same F cosine, is not enough to overcome force of friction here. That means that Art must have more friction than Bill, because here it's enough to move, here it's not enough to move. Now let's think about, we find force of friction, the maximum force of friction is mu Fn. They are on the exact same surface, and that means it's the same coefficient of friction, right? So the coefficient only depends on the material. But they do not have the same normal force. So Art, his normal force is Fg plus F sine, whereas Bill, his normal force is the Fg minus the F sine. So Bill has a much bigger Fn, which means it has more or a greater force of friction, which means it's harder to move. That would explain why when you push with the same force, it doesn't move, but this one does. So our explanation is that Art is pushing down on his box, which leads to a greater normal force on the box. And I would make in parentheses because your normal force is the gravity plus the F sine. So it has a greater maximum static friction force, because force of friction is mu Fn. So I'm just putting the relationship, right? Force of maximum static friction force is mu Fn. This one has a greater Fn with the same mu, so it's going to have a greater static friction force. So it needs more applied force to move. And then you can say the opposite about Bill, right? Bill has less Fn, because Fn here would be mg minus F sine. So it has a smaller static friction force, so the F cosine is enough to move it. Alright, number 2. So a lot of people got confused on this diagram. He is not hanging, he's like standing. This just means it is being pulled with an applied force of 1 Newton. So I'm going to redraw my diagram with all the information. So this just means pulled with 1 Newton. This is scenario 1. Scenario 2 is super similar. I'm going to put the mass, so 1 Newton would be, this is the weight, right? So this is the Fg, so then the mass would be divided by 10.1. So this is 0.1 kilograms, but it's still a weight or a pull of 1 Newton. Now, each system is being pulled with 1 Newton. The difference between the system is that in the first one, it's only the cart being pulled with 1 Newton. Whereas number 2, it is both the cart and this hanging mass that are pulled with 1 Newton. So if we're thinking through which one has the greater acceleration, well, they both have the same force. So they have, I'm going to say, they both have the same force pulling on the system, but one has less mass to pull, so it'll have a greater acceleration. Because your acceleration is F over m, right? If this is the same for both, but then smaller mass, you would have a greater acceleration. There is an argument to be made. Some of you drew like free body diagram for each of these. So this would be tension and this would be tension. Because this is accelerating, you know your tension here is less than the 1 Newton, which means this right here is less than 1 Newton. So then this car being pulled with less than 1 Newton compared to being pulled with 1 Newton, the 1 Newton would have a greater acceleration. I just thought about it as a system as a whole. Same force, less mass will have a greater acceleration. All right, here we know this is the biggest mass, then this one, and it says ignore friction. So the only forces pulling on the system are the 2 gravity forces. This force of gravity is not as much as this force of gravity, so then that means the system is gonna, this side wins, right? So this guy is gonna accelerate down, this guy will accelerate to the right, and this guy will accelerate up. So I need to make sure that when I'm drawing my free body diagrams, I have block 1 accelerating up, I have block 2 accelerating down, and I have block 3 accelerating to the right. I have 2 different strings here, which means I'm going to have 2 different tensions. I'm going to call this T1 and call this tension T2. Let's start with our free body diagram on block 1. So it has the smallest mass, so I'm just going to make it small mass, or small force of gravity, F2, or Fg. And then I'm going to make the tension T1 greater than that. So I have the gravity force as 2, so I need to make the tension force just a little bit bigger, T1. So I made that 3 units long. Now let's go to, I'm going to jump to block 3 because that's the easiest, I think. It has a greater gravity, but it's balanced out by the normal, so it doesn't really matter. I need to make sure these are balanced. Okay. Fn and Fg. Now, block 3 is being pushed, pulled with the T2, so I'm going to have T2 going this way, but I have T1 pulling against it. That T1 is the same T1 that is pulling up on block 1, so I need to make sure that this is the same length. So 1, 2, 3, 1, 2, 3. So I have T1 like this, and then my T2 needs to be greater because I know it's going to accelerate to the right, so I'm going to make it like 5, I don't know, 1, 2, 3, 4, 5. Doesn't matter. As long as it is greater than T1 so that it is accelerating. And then now I need to go to block 2. Block 2 has a force of gravity and also feels a tension force. So the tension force pulling up is the T2, which I made 5. This is T2, but I need to accelerate down, so I need to make my gravity force more than 5. So 1, 2, 3, 4, oops, 6. So things that, like when it has the free body diagram and it has the grid, that is, and it tells you, make sure you reflect the magnitudes, that means make your links meaningful. So I should always be able to tell which way it's accelerating. So this one accelerates up, block 2 accelerates down, and 3 goes to the right. So that checks out with each of these. And then T1 is the same T1 right here. These need to be the same length. T2 is the same T2 right here. These need to be the same length. All right, deriving an expression for the acceleration of block 3. They all have the same acceleration, so it doesn't matter if it just said of the blocks. And I'm allowed to use the masses, and fundamental constants basically means G, right? Physical constants, fundamental constants. So I'm going to draw write my F-net equation for each of these. So F-net will be M1A, this one will be M2A, this one will be M3A. For block 1, tension is greater because it accelerates up, so that would be T1 minus M1G. For block 2, that's going to be gravity minus tension, so M2G minus T2. And for this one, it is T2 minus T1. All right, I need to kind of combine these equations, so I'm going to get T1 by itself. And I'm going to take that and I'm going to substitute that in. So here's the T1, I'll substitute it over here. So So M3A is T2 minus M1A minus M1G, because that negative sign gets distributed to all of this term. And I'm going to add these over, so that's M3A plus M1A plus M1G equals T2. And now I can take that and substitute it in for T2. M2A equals M2G minus all of this. And now I just need to get A by itself, so I have these A's. I cannot just divide over, because you can't have A equals and then have A's in your answer. That doesn't make sense, so I'm going to add these over. So I have M1A plus M2A plus M3A equals M2G minus M1G. Now I'm going to factor out an A, so I've pulled out the A, and now I just divide by this term. So A is the M2G minus M1G over all your masses. And then we should stop and think, like, does this make sense? Because it definitely should. So here, the forces pulling on the system are the two gravities. They're opposing each other. This one wins, so it would be this weight minus this weight, M2G minus M1G. And then those two forces are acted over the total mass of the system, M1 plus M2 plus M3. So here, right, if I wanted to make this go faster, I would increase M2, because M2 is going to make a greater pulling force. If I increased M1, that would mean more pulling force against, which would be like a smaller force on the system. If I increased M3, that's not changing the forces pulling the system, but it is making it harder, more mass to pull, so that would make it go slower. Alright, if there were friction between the table and block 3, which way would the direction force point? So the block, if I had it sitting right here and I just released it from rest, the block wants to move to the right. So block 3 would move to the right. So force of friction would be to the left, because force of friction opposes motion. Alright, the next one. M2 is on a frictionless table. It's going to be released. M1 is over this frictionless pulley. Draw the forces on each block. So M1 and M2. So M1, let's decide which way it's going to accelerate. So this guy only feels the tension pulling it horizontally, nothing against it. So this guy's going to accelerate to the right. This guy's going to accelerate down. I completely understand that this is a small mass pulling a big mass. If it was the case where they were hanging, right, they were both hanging, then this one would win. It would accelerate this way. This guy is not pulling against, it's not like its weight is pulling against this guy's weight. It's just like more mass to pull. So it will slow it down, but it doesn't mean it will cause it to accelerate up. So it's still going to accelerate down like we expect. If there were friction, then it's possible it wouldn't move, but it would not cause it to accelerate the other way. So it's either accelerating down or there's enough friction to hold it in place. That means that if this is accelerating down, the force of gravity is greater than the tension force, so this tension right here. Now M2 has a big gravity force, but it's sitting on a surface, so it also has a big normal force. And then it feels that same tension pulling it to the right, and there's no friction, so there's nothing pointing against. Now I want an equation for the acceleration of M2. Again, these are connected, so it's the same acceleration, so I just want whatever the A is. And I'm allowed to have the two masses in G in my answer, nothing else. So I'm going to write my net force equation. M1A is going to be gravity minus tension. M2A is just going to be tension. So I take this, substitute in, M1A equals M1G minus M2A. And then I'm going to add over, because I need to get my A's together. Now I'm going to pull out an A, I'm left with M1 and M2. And then divide over M1G over M1 plus M2. That's my acceleration. And this should make sense because the force that's pulling the system is just the gravity force divided by the total mass of the system, the two masses together. right, if I wanted to have the greatest acceleration possible, which mass would you increase using both equations and not equations? So let's do without first. So without equations, if you want this to go super, super fast, then I want this mass to be huge. I want this one to be pulling a lot. Because see how this M1 is the one whose weight is pulling the system? So you want to increase M1 because the force of gravity on M1 is the force that is pulling the system. So if you increase the mass, you have a greater Fg pulling on both M1 and M2. And a greater force would mean a greater acceleration. I'm going to come back to the with equations. So now let's talk about smallest acceleration possible. If you want the smallest acceleration possible, then you want to have not a big mass here, you want a small mass here, you'd have a huge mass here. Because although it's not like pulling against it, right, it's not like counteracting the weight, it is just providing more mass to pull, making it harder to pull. So here, if I want to, let's do without first, I would want to increase M2 because then you would have a small force of gravity of M1 pulling on a big mass 2, which doesn't counteract, but it does make it provides more resistance, it's harder to pull. So that is harder to pull, which is less acceleration. Now using our equation, so with my equation, so I have m1g over m1 plus m2. If I increase mass 2, see how I'm keeping the exact same force, but I'm dividing by more mass. So this is just going to, if you increase m2, you have a smaller denominator, which means I said that wrong. You definitely, if you're increasing this, you have a greater denominator, which means a smaller or less acceleration. So if you increase this, you're dividing by greater numbers, so that would make your acceleration smaller. Because think about, like, if this was like 1g over 1 plus 1,000, right? You just got really small. It's 1 over 1,001, which gets really, really big. Now, the equation here is a lot trickier because you actually have m in 2 places. These cannot cross off because you don't have an m1 in this term, right? You can't cross off unless it's in every term, so they don't totally cancel out. But it is like kind of a direct relationship here and also indirect relationship here. So let's think about if I had like actually let's not talk about that quite yet. So think about if I'm increasing m1, then this will go faster. If I make a greater force right here, that will make it go faster. We talked about in class yesterday, there's a limit to it, right? Like I could have 1 million pounds right here, a huge mass, and pull like just 1 pound right here, and that's not going to be going at like a crazy fast acceleration because the fastest acceleration it can get is just g, right? If you don't have anything, it's going to fall at g. So if I just have the tiniest mass that's only providing a tiny resistance that's really, really close to g or 10. That's reflected in our equation because see if I had like 1,000 g over 1,000 plus 1, 1,000 g over 1,001, that's just a teeny tiny bit under 1, basically is g right here. So for this equation, I'm actually not going to do it with equations. I kind of regret putting it here. I wanted to, it's a lot harder to explain, so don't worry about your explanation with equations here because it gets complicated because you have both the direct relationship here and indirect, but I want you to realize that like this one here. So here, increasing on top made it go faster, even though you're still dividing by a smaller number.
No, she's in here. Thanks.
Hey, I'm making a video right now. You're walking through it.
Hi, everybody. Listen to Miss Campbell. She's awesome.
Okay. Hey, I have one more question. I'll come back. All right, number 5. So we want to determine the coefficient of static friction. So I'm looking for mu between this little m and this big M right here. this angle can change, so it's gonna start flat and it's raised until the exact angle where the mass, where the mass stays in place. So stays in place tells me this is at rest, my forces are balanced. And specifically, this is exactly